Hello, this video is an overview demonstration of the respiratory model and simulation platform. So this program is an interface for a respiratory model generation algorithm. This codebase has been organized to support better models in the future, and this just serves as a foundational platform to build those on. So I'm just going to give a quick demo of how things work, explain a couple of things. If you want more details, you can look at the repository, and there is a nice README explaining how to set this up and run it yourself, the project structure, and how the actual algorithm functions. So anyway, I'm going to run the graphical user interface, and I'm going to provide a config, which is going to be, I'm going to decide the left lung using a CT scan, and I'm going to provide a preset just for viewing. This is the graphical user interface, and as you can see, there are a lot of options, so I'm going to go through them briefly. So to start off, the way that this algorithm works is it takes a object file, which we have here sourced from a CT scan, and it computes a voxel volume in order to optimize understanding where the volume actually lies and which points lie within the volume of the mesh. And what that looks like, if I show the point cloud and I disable the mesh, these red dots represent discrete space points, which allow us to index the boundary for the volume. Then we can compute using a foam filling algorithm to understand the actual solid internal of the volume, which looks like this. If you see any gaps, this is because I only sample 128,000 of these points so that I don't crash the computer. But anyway, next I'm just going to demonstrate the actual airway model, which looks like this. The algorithm for how this works can be seen again in the README. But this is 16 generations. If I increase the number of generations to, say, 30, and then update the scene, as you can see, we get more airways. I can highlight the terminal airways, which will be in purple. These terminal airways represent where the simulation creates limits determining when airways should stop recursively generating. So there's a couple of reasons this may happen. Sometimes it's because of the length. Sometimes it's because of the simulation not being able to have any more points to evaluate. Either way, I'm going to show you some more cool things that this interface can do and how optimized it is. If I run the continuous compute loop, this allows me to actually make changes live. So I can mess with some of these here, such as the homothency ratio. This is essentially a ratio relationship between parent and child branches and how thick they are. I can also change things such as the angle limit and cause things to rotate and get all messed up. The reason I'm doing this is mainly just to show how optimized the algorithm is. As you can see at the top here, we can see the total branch is 107,000, and that's at 19 generations of compute. I can raise this value even further, such as to 25, and then I can adjust the same values, and they will update relatively quickly. Even more than that, I can select a specific subcollection. If you look at this diagram, it demonstrates these things that I call subcollection IDs. What they are is a mathematical representation of which branch relates to the parent and children on the tree. So here, for example, 8 has two child branches, 18 and 20, and the parent branch is 2. And we can mathematically determine this by using some arithmetic. So here I select branch 8, and as you can see here, the immediate children would be 18 and 20. So if I were to select either of these, we'll bisect it, and we'll only be looking at one of the child branches from this. And we can continue to do this. And as you can see, if you focus on this area, it continues to bisect, and we're focusing more and more deeply on the airway tree. And this is beneficial because it allows us to increase the resolution of the simulation, such as maybe decreasing the length limit to permit smaller branches to be generated. But it's telling the simulation it only needs to execute up to this point. And right here, the branch that we have selected, this is the sub ID of 318. This branch is the parent, and so all the children will get generated, and any other branches that are also on this generation will cease to be bisected. Yeah, and I suppose the next thing I'll do is I'll just showcase the same thing, but for the right lung. Back at it again. Click update the scene. There you go. There's a bunch of different things in here that you can play around with, and there's a lot more to this algorithm that I'm showing here, but this is a decent overview of how the program works. I intend for this to be a flexible platform, and the next steps I anticipate will be building better models. This model functions by using mostly continuous space mathematics, and that can be computationally inefficient and also leads to some interesting problems with the concept of space filling. Some of these branches at higher iterations will end up conflicting with each other, and floating point precision has only so much capacity that it can offer. So by moving to more to a voxel model, I'm hoping to replicate the results of this airway, but at far deeper, but at far higher precisions and far more medical accuracy. So this will be a nice foundation to compare what we do in the future. And yeah, I suppose that's it.